Right, let's dive straight into this explainer and decode the fascinating, highly structured world of plain bearings. If you've ever marveled at the sheer reliability of heavy industry, well, you're actually admiring the quiet, unseen work of these absolutely vital components, and, of course, the catastrophic failures they prevent.
I mean, just look at the sheer scale of this train. To keep massive machines like this moving without literally destroying themselves, we have to conquer the absolute enemy of mechanical engineering: friction. Almost all industrial mechanisms contain elements that require relative movement between contacting surfaces, don't they? And without the right mitigation, that metal-on-metal movement generates catastrophic heat and wear.
So here's our roadmap for today. 1. The battle against friction. 2. Meet the plain bearing. 3. Plain thrust and linear bearings. 4. The materials that matter. And 5. Best practices for maintenance.
Okay, let's jump into Section 1, the battle against friction, understanding mechanical loads.
You see, the function a bearing performs is largely dictated by the type of load it has to carry. Understanding the type of load is step 1, really, because it dictates exactly what kind of bearing we're going to deploy. A radial load pushes down perpendicularly onto the shaft. An axial load pushes along the length of the shaft. We often call that thrust. And a combination load, as you'd guess, applies forces in both directions simultaneously. Grasping these forces is absolutely crucial to keeping any machine running smoothly. Moving right along to Section 2, meet the plain bearing, the core concept.
Now, the crucial takeaway here is that unlike other designs you might be familiar with, a plain bearing relies purely on two surfaces sliding directly over one another. That means no balls, no rollers, just an elegantly simple category of bearing where the surfaces in contact are especially prepared to minimize friction and wear. They often come in the form of a solid journal bearing, which we call a bushing if it has thin walls, or a sleeve bearing if it's thick. For easier maintenance and shaft removal, we use split bearings designed in halves. And for heavy, constant direction loads, we use partial segments that only support the shaft from the bottom.
There's a brilliant engineering choice to make here regarding lubrication. For general support, full film lubrication is fantastic, but the film thickness tends to vary. What if we need extreme precision, say for machine tool carriages? Well, in that case, full film is actually undesirable. Instead, we rely on boundary lubrication. This allows just a tiny bit of metal-to-metal contact, which helps us locate the sliding element far more accurately.
But hold on, if we allow metal-to-metal contact, doesn't that cause wear? Well, yes it does, and that leads us to a golden rule of mechanical maintenance. Think of the plain bearing as a sacrificial protector. It's intentionally designed to wear out first, so the incredibly expensive shaft survives. It's basically engineering altruism at its finest. It sacrifices itself slowly over time to protect the difficult-to-replace journal it supports.
Right, let's see how these are adapted for different movements in Section 3. Plain thrust and linear bearings, guiding motion.
Take a look at the specialized radial grooves on this plain thrust bearing. It restrains axial movement by using a stationary pad that the rotating element bears against. Remember those axial forces we just discussed? This bearing takes the end thrust of a shaft. What's truly fascinating here is the fluid dynamics at play. Lubricant has to be fed into the inner diameter so it flows outwards across the bearing face through these exact grooves. And because of this reliance on fluid flow, the maximum running speeds of these bearings are strictly limited by the viscosity of the lubricant used.
Now, for straight-line reciprocating motion, linear bearings, often called ways or guides, use geometric shapes like V-angles and dovetails. These support linear or curvilinear motion rather than a rotating shaft. The V-angled shape provides a brilliant directional guide and support, whilst the dovetail variation can be finely adjusted using a parallel jib and set screws.
Let's peel back another layer and look down at the metallurgical level. Section 4. The materials that matter: white metals, copper, lead, and bronzes.
Engineering is always about trade-offs, isn't it? A plain bearing material has a really paradoxical job. It has to be hard enough to resist wear, yet soft enough to conform to the journal during the running-in process. White metals, or Babbitt alloys, have amazing conformability and embeddability, meaning they safely absorb rogue dirt particles so the shaft doesn't get scored. But their fatigue strength drops off a cliff at high temperatures. Copper-lead alloys, on the other hand, provide up to 4 times the strength, but they lack that soft conformability. That's actually why they're sometimes overlaid with a thin layer of white metal in a tri-metal setup. And finally, you might choose economical bronze, which can be tailored with a huge range of properties for different environments.
So, how do we keep all this running? Let's step into the shoes of a technician for Section 5. Best practices for maintenance, caring for plain bearings.
The absolutely critical point for general maintenance is cleanliness. Dirt and moisture are absolute destroyers that will cause severe scoring, pitting, and corrosion inside the bearing. If you neglect this or suffer from lubricant breakdown, you'll quickly run into operating symptoms like overheating, severe vibration, noise, or ultimately, total seizure. Also, always mark your parts before disassembly. Why? Because during the running-in phase, the soft bearing material essentially marries the specific microcontours of the shaft. If you swap them around during reassembly, they simply won't fit right and will fail. You've also got to ensure perfect alignment and strictly follow the manufacturer's bolt tensioning specs to get the proper bearing crush and clearances.
Let's look at a concrete procedure, like a press-fit assembly for bushes. You start by checking dimensions and, again, ensuring absolute cleanliness. Now, step 3 is a big one. Absolutely no hammers. Hammering shocks the material, leading to internal failure symptoms like galling, fretting, or wiping of that soft alloy. You have to use an arbor press and push the bearing into the housing using one continuous, lubricated motion. After it's seated, you check for close-in, which is when the inside diameter shrinks slightly from the pressure of the fit, and finally you hone or ream the bush back to spec.
Now, if you're not using a mechanical press fit, you can go for a shrink fit, which relies on thermodynamics. Instead of pressing the bearing in, you uniformly heat the housing to around 100 degrees Celsius. This expands the metal just enough for the bearing to slide in effortlessly. Once the housing cools down, it shrinks and grips the bearing incredibly tightly. But be super careful not to heat the housing any more than is absolutely essential, or you'll warp the metal. Once everything is installed and cooled down, you must verify those final bearing clearances using precision tools, like micrometers, Plastigage plastic thread, or shims, to make absolutely sure it's ready for safe operation.
So, having seen how these perfectly structured components take the absolute brunt of mechanical wear, it leaves us with a really compelling question. As loads increase and speeds accelerate, what innovative new alloys will be required to protect the heavy machinery of tomorrow? The humble, sacrificial plain bearing is going to have to keep adapting. It's a fantastic reminder that sometimes the most critical part of a massive machine is actually the softest component inside it. Thanks for joining me for this explainer, and keep your curiosity turning.